Once again, welcome to the session.
Thank you.
Dear participants, as I have already mentioned, we construct the hypothesis to test whether we reject the null hypothesis or accept the null alternative hypothesis. And as I already mentioned, we test only null hypothesis. If we reject the null hypothesis, then we can go for alternative hypothesis. If you cannot reject the null hypothesis, we are not accepting null hypothesis, simply we are not going to accept the alternative hypothesis. Meaning, we can reject null hypothesis or we cannot reject null hypothesis. These are the only possibilities. If you reject null hypothesis, then you go for alternative hypothesis and you prove your research hypothesis. Your alternative hypothesis, it's a research hypothesis. For example, you're going to prove some differences, some relations, some impacts, some associations. So that you can make as your alternative research hypothesis. While doing this kind of the testing of hypothesis, generally we do commit two types of errors. That is type 1 error and type 2 error. While conducting hypothesis testing or while making the arguments or making the decisions while testing the hypothesis, generally we do make two types of the mistakes. One is type 1 error and another one is type 2 error. Type 1 error is rejecting null hypothesis when it is true. Reject the null hypothesis when it is true. Null hypotheses are always like no difference, no relations, no impact, no association, no skew. These are all the format of null hypothesis. No difference, generally you make no difference, no relations, no impact, and no association, and there is no skew. So these are the 5 different types of the hypothesis, null hypothesis, generally you can construct. Okay. Alternative hypothesis, there is significant difference, there is significant relationship, there is significant impact, there is significant association, and there is significant skew. These are all the alternative hypotheses. For your subject, for your research subject matter, you can construct different hypotheses, but the basic structure of the hypothesis will be like that. No, no, no. Yes, significant difference, significant relation, significant impact, significant skew, and significant association. So here, as I already mentioned, we test only null hypothesis, and according to the tested proof, you may not reject the null hypothesis. So you are not supposed to reject the null hypothesis. Okay, meaning you are not having sufficient evidence to reject the null hypothesis. But if you reject the null hypothesis, even though you are not having sufficient proof or sufficient evidences to reject the null hypothesis or the tested proof for rejecting null hypothesis, you are not having. Even then, if you reject the null hypothesis just to prove your alternative research hypothesis, that's a kind of type 1 error. That is type 1 error. That's the mistake you are conducting. In another case, type 2 error, accept the null hypothesis when it is false. False means you have a lot of evidences to disprove the null hypothesis. You have a lot of evidences to disprove. That is no, no, no. So to say no, there is no. You have a lot of evidence to disprove the null hypothesis. Even then, if you accept the null hypothesis, that is a kind of error which is known as type 2 error. So generally, we do these 2 types of the errors. Why I am saying like this? There is a margin for every argument. So since even it's science or even it's social science, commerce or management, 100% of precision cannot be ensured. Even in the science, you talk about the under the laboratory conditions. If you go and do the same test in different laboratory situation, you will get different values. So in the same way, in the social sciences, if you go to field, if you get the same kind of the data, you make the analysis, even then there are some randomness in the data. So because of this randomness, we cannot go with 100% precision for our argument. At least 90% of the reliability, 90% of the confidence, 90% of validation, are the 90% of supporting your argument. So therefore, there are two parts. One is the confidence in rejecting or accepting the null hypothesis. And the second one is, well, accepting or rejecting the null hypothesis, what is the allowable error that you can commit? Okay, what is the allowable errors that you can commit? So that allowable error should be minimum, and the confidence, the level of confidence should be more. The level of confidence should be more while you accept or reject. While accept or reject, the confidence should be more and the margin of error should be less. So generally, we go with 95% of the confidence in any decisions. If you have 95% of the confidence, if your margin of error or the probable allowable errors in your decisions is 5%. Okay, in any accept or reject, this is the criteria. You should have 95% of the confidence and your error should be less than 5%. So when we always theoretical foundations, what is the theoretical foundations? If you repeatedly conduct 100 times, for example, if you conduct 100 times yes repeated sample, if 5 times if you do any mistakes, that is not a big mistake. So having said that, we having that theoretical foundation, we allow 5% errors in our decision making. So in any conditions, whatever the conditions, in any conditions, if the margin of error, is less than 5%, meaning the margin of error is only 4%. The margin of error is only 4%. Got it? Margin of error is only 4%. Then what happens? Your level of confidence increases. The reliability in your decision increases. The level of significance increases. Okay. So as well as the margin of error decreases, the confidence increases. When the confidence increases more than 95% and the margin decreases less than 5%, you can reject your null hypothesis. If you are rejecting the null hypothesis at that point of time, when you have more than 95% of confidence and less than 5% of error, if you are rejecting null hypothesis, then you are not making any error. Then you are not making any errors. Meaning your decision of rejecting null hypothesis, accepting alternative hypothesis is right. Okay. If your confidence is less than 95% and your error is more than 5, even then you are rejecting null hypothesis, that is not right. If your confidence is less than 95%, your error is more, even then if you are going to reject the null hypothesis, that is not the right decision. So meaning you are committing type 1 error. So therefore, in any decision making while conducting a testing hypothesis, if your level of confidence is more than 95% and your error is less than 5%, then you can reject the null hypothesis and accept the alternative hypothesis. So in the same way, in the type 2 error procedure, we have test value. The test value is that at the point of 95% of confidence and the 5% of margin of error, you have a test value, table test value. You have a table value. If you're conducting t test, you have a t test value. If you're conducting f test, you have a f test value. If you're conducting chi-square test, you have a chi-square table value. And at the same time, when you calculate the test value for your problem, for your testing, the calculated test value, it may be T, F or chi-square, the calculated test value should be greater than the table value. These are the two criteria we always use while testing the hypothesis. Let me repeat once again. Your confidence should be more than 95%. The margin of error should be less than 5. That is the p-value. The p-value should be less than 5. Less than 5 in the meaning, it should be less than 0.05. Because probability will go with 0 to 1, so that the probability of committing type 1 error or the probability of margin of error should be less than 5, meaning it should be less than 0.05. And the probability of your confidence should be more than 95, meaning should be more than 0.95. That is one condition. The second condition, your calculated test value should be greater than the table value. So if that is the case, then you are not making any mistakes. You should have this. Okay, let us see the distributions. So distributions, why I'm talking about the distribution here, it is when you are conducting the t-test or f-test or chi-square test or any test, or the difference test, correlation test, regression coefficient test, Q-ness test, whatever all the tests you are conducting the test based on certain distributions. So therefore, distributions matters. Without distributions, there are no tests. Without distributions, there are no tests. Sorry. There are many probability distributions, but most of the tests are designed in the background of theoretical distributions. And most popular distributions are normal distribution, T distribution, F distribution, and chi-square distribution. So for the normal distribution, it is a symmetric kind of the distribution. The shape of the curve is bell-shaped curve, and the normal distribution has constructed by using the population. Am I right? The normal distribution has constructed based on the using the data, population data. When you have talk of population data, for the population there are no tests. Am I right? For the population, there are no tests. I have already mentioned why the population cannot be tested, that I have mentioned. So since it's a normal distribution and the normal distribution has used population data, there are no tests designed to test in the background of normal distribution. Okay, then we have sample based theoretical distributions like Z or T distribution, F distribution, chi-square distribution. We do conduct all our tests in the background of these three distributions. So Z or T distribution. T is a sample, small sample distribution test, and the Z is the large sample distribution test. And we use T test or the Z test to test the mean differences. Mean differences, meaning it is the mean test. The T test is also known as the mean test. What are all the tests we have? The T test, we have one sample T test, we have two sample T test, we have paired sample T test, right? And then we also use the T test for testing the correlation coefficient, and you also use the T test to test the coefficient of regression coefficient. T test is largely used test. T test. Okay, and the shape of the T test is also like this. It is also like the normal distribution, And also, as I have already mentioned, we use this T test only for the parametric data, meaning only for the ratio scale. The test is parametric. And what are all the tests you are conducting T, it is the mean test. And then F distribution. Yes, F distribution is a single-side distribution. F and chi both are single-side distributions. And we use the F test or the F distribution for conducting F test. And the F test again, it is a parametric test. And F by default, we use it to test the variances. The variances. So F distribution, we always use to test the distributions, variances. So F test meant for variance test. So what are the tests? We do conduct the F test for ANOVA test, that is more than two group mean comparison test, significance of the model, that is the F test for the whether the independent variables used in the model are significantly explains the variance in the dependent variable. For that also we use the F distribution test. And then lastly, chi-square test or the chi-square distribution. It is also single-sided distribution, and it is used for non-parametric tests. The Z-T and F distributions are parametric tests. You have to use ratio scale data. There is no options. There is no options. You have to use, because they are parametric means you have to measure. You are measuring. Whereas non-parametric, you are not measuring. Meaning, you have to use only nominal data for the chi-square test. So nominal data like yes, no, male, female. When you have data of nominal kind, then you can go for the chi-square distribution. And it's also known as non-parametric test. So these are the three popular major distributions we have to conduct any type of the test. So, and there are 7 steps in the hypothesis testing. One is formulation of hypothesis, that is construction of null hypothesis and alternative hypothesis. Repeatedly, I have told that null hypotheses are no difference, no relations, no impact, no association, no skew. That's very important. For each of the tests, we use data, and you should know what is the data. Is it a nominal data? It is a ratio scale data largely. So we use these two types of the data largely, that is nominal data or the ratio scale data. If it is a nominal scale data, what distribution you have to follow? If it's a ratio scale data, what distribution you follow? Generally, as I already mentioned, if it's a nominal data, you have to go with chi-square distribution. If it is a ratio scale data, then you have two options. Are you going to test the mean or going to test the variances? If you are going to test the mean, then you go with t-test. If you are going to test the variance, you have to go with the F distribution. And then the third one, you have to decide the test criteria. Sorry. The test criteria I already discussed in the previous section. That is what is the level of significance. Level of significance means what is the margin of error that I can allow. Whether it is 5%, 1%, or 10%. And you have to decide. The most of the science people, they go with 1% or 5%. In social sciences, we go with 5% and 10%. Sometimes you also go with 1%. It all depends. What is the severity of accepting or rejecting a phenomena? For example, just let me give you an example. There are 100 people suffering from cough like me. And one doctor says, this is very good medicine. If you all 100 takes, 99 people will be cured. And there is a chance of 1% to die. Will you take that 1% as the level of significance? No. So if out of 100, if 1% is going to die, you are not going to take the chance. So then the margin of error should not be even 1%. It should be less than 1%. Okay. Even in the case of COVID, when they have tested and given the vaccinations, they have given out of 1 lakh or 10 lakh, 1% may be suffered. So that is the case we go. So like that, it all depends on what is the severity of the phenomena that you are going to test. If the phenomena is very, very serious, then you go with 1% or less than 1%. If the phenomena is normal, you can go with 5% level of significance. And you're also going to tell, so what is the tile? Are you going to test the hypothesis with one tile or two tile or right tile or the left tile? And what is the degrees of freedom that you are going to use? So degrees of freedom is also important because as the degrees of freedom changes, your table test value will be different. And then fourth step is computing test statistic. That is, nowadays you can manually compute or you can use SPSS to compute the test values. So it is not a big thing. So if you know the steps involved in testing a hypothesis or making a test in the SPSS, in just 1 minute you can test and you get the test results. I will show you the next slides. I will show you how to get the test statistic because it is very, very important. We cannot go with p-value method. There are two methods. One is the p-value method, another one is the level of significance, test level of significance. So in the level of test significant, manually whenever we do conduct the test, we compute the test value and make the comparison of that test value with the table value. If the calculated test value is higher than the table value, then we reject the null hypothesis. I have already mentioned. And then comparison and interpretation. So what we do, the fifth step, we compare our calculated value with the table value and make the comparisons. And based on the rules, regulations, whatever already I have mentioned, based on that, we make the decision. We make the decision whether you are going to reject the null hypothesis or accept the alternative hypothesis. Reject or accept the alternative hypothesis. And then when you have make the decisions, then you going for drawing the inferences. So if there are differences, you say, yes, there are significant differences between the male and female students in their marks. Yes, there is a significant relationship between income and consumption expenditures. Okay, like that you will make the inferences. And you can also make, yes, income has significant impact on consumption expenditure. Okay, that also you can make. So that you will draw some inferences out of your decision made against the test. So once you have made draw the inferences, then you can go for the policy imperatives or the policy suggestions. Okay, so the policy suggestions, it should be based on your decision. Okay, what is that? For example, let me tell you one real example. So we have selected a district where yeah. So let me give an example. There is a backward region where the newly born babies are underweight. So I thought of conducting a survey. Let us see what is the weight of these newly born kids, babies, and I have found that the average weight of the newly born babies in a underdeveloped district is 2.3. And I have seen that the national average of the newly born baby's weight is 3 kilos. Then I thought, oh, really, there is a problem in this backward district. Then what I do, I compare the average weight of the newly born babies in that backward district with the national average, and I proved that yes, there's a significant difference. Then what I do, I suggest. So there's a need of introducing the program to improve the mother's health in order to increase the weight of the babies. Like that, you can give some policy suggestions. So anyhow, we give suggestions based on our tested proofs. So that while giving proofs, you have to have lot of support, tested supports. So the once you have tested supports, you are free to make the suggestions, and any kind of suggestions you can do. Okay, so these are all the theoretical parts I have explained. I have explained about the data, the different types of the data, particularly based on the scale of measurement. Nominal data, ordinal data, interval, and ratio scale data. Each has its own properties. That's very, very important. because tests have designed for different scale of data. If your data is nominal, the test becomes different. If your data is ratio, the tests are different. So if your data is nominal, then you can go only with chi-square test. If your data is ratio scale, then you can go with T or F test. So therefore, understanding the data, it's very, very important. Once you have understand the data for what you are going to test. So are you going to test the difference? Are they going to test the relations or the impact or the association? So based on that, you have to construct the hypothesis. Once you have constructed the hypothesis, you have to test. So while testing, generally you do two types of the errors, type 1 error and type 2 errors. So in order to avoid this committing type 1 or type 2 error, you have to have lot of confidences. That is, the level of confidence should be more than 95% and the margin of error should be less than 5%. That's the next thing. And then when you are really conducting the hypothesis, so you have to conduct the hypothesis background of some distributions. So if you're conducting T test, you are going with T distribution. If you're conducting F test, you are going with F distribution. If you're conducting association or the goodness of fit test, you are going in the background of the chi-square distribution. For parametric, you use T or F test. For the non-parametric, you use chi-square distributions. And after that, you have a procedure of conducting, starting from the hypothesis to decision making. So now you have an understanding of how to conduct the test. So let me now go one by one, how we can do test. Okay, I'm taking some circumstances and hypothesis and try to make the comparison. So the first circumstances is what the first example I have given. We have some sample, observation. What our example I given, background district, weight of the newly born babies. We have only sample observations, and we also have a national average. The national average was 3 kilo, and the sample observation is different from the national average. So that is the case. We have a sample, and there is a national average. In that is the situation. Let me go to the next slide. Okay. If that is the situation, look at here. We have population, and we have a sample which is drawn from the population. The sample is drawn from the population. Okay. And for the sample, we have a value, and for the population, we have a value. Sample is it is the observed value. Sample is the observed value. Even for the science people, they have repeatedly conducted the same test 30 times, 20 times. They have got different readings. Okay. And there is a standard reading, and you make the comparison of all these 30 with the standard reading or the standard value. So as I have given the examples, in the backward districts, there are there are babies. I have taken 100 babies or 200 babies, and you have the data for the 100 babies and 200 babies. And then you go to make the comparison of this sample average with the population, populations. Okay. So this is the situation. Then you have to go with one sample T test. And this is the T distribution. And you're going to say two things. And you're going to make the decision of two things. One is there is no difference between the population and sample in their mean value. Mean means average value. Okay. There may be differences, but these differences are not significant because the differences are only because of the random chance. Meaning there is no difference between population mean value and the sample mean value. Right? So otherwise, if you have proved this, meaning you are not rejecting the null hypothesis. If both are same, you are not rejecting the null hypothesis. If you reject the null hypothesis, meaning the population average is different, the sample average is different. Okay, I have already mentioned the conditions. Okay, let me go to whether the rate of profit of, just an example I am giving, whether the rate of profit of food processing companies is on par with the national average. So there are food processing companies and making profit, and but the profit of each of the company is different, right? Like that, marks of each student is different, and there is a national average, and there is a school average. In the case of marks, what are the example I have given? The marks are different, and there is a average marks of the school, like that. How do I construct the hypothesis? There is no significant difference between average profit of food processing companies and the national average. Here the main thing is there is no significant difference. There is no significant difference, meaning I am going to conduct the difference test, mean difference test. I am going to conduct the mean difference test. Mean of what? One is population, national average, meaning one is the population, and the food processing companies, these are the samples. So I have only one sample group. I'm going to make the comparison of this sample group with the national average, that is population average or the population mean. And alternatively, what I write for the alternative hypothesis, there is significant difference. Here there is no significant difference, whereas here there is significant difference. So, and then as I already mentioned, you should know test criteria, 5% level of significance, meaning the allowable errors in your decision, it's only 5%. And it is two type, because I'm talking about there is no difference. I'm not going to talk about the sample value is higher than the population value, then right tail test. The sample value is less than the population value, then it is the left tail test. I'm not going to do that. Just I'm telling there is a difference between population mean value and the sample mean value. Then I am going to do with two tail test. And the data is numeric. So I already mentioned this is a parametric test. It's a parametric test. You have the weight. Weight is ratio scale. The rate of profit is a ratio scale. So it's a parametric test. So the numeric data I have given the Excel sheet, but I am not showing here. Okay, I have taken the data. So there are companies and their profit is starting from first company 12.39, 10.4, something like that. There are different, 8 is there, 13 is there. So this is the data I have. This is the sample data. These are all the sample observation for the profit. Profit is a single variable, and I have many observation for that. Right? And now I am going to test this profit, rate of profit, with the national average. Sorry. As I already mentioned, sorry. As I have already mentioned, we have a lot of softwares to conduct the test. You need not worry to compute. So if you directly go and compute, then you write the T formula x bar minus mu divided by the standard deviation by n number of observations. So that's the formula. By using the same formula, the softwares have designed the program, and you can directly get the results. So here I have results. And what are the results? The sample mean value is this. The sample mean value is 12.11, right? And the test value is nothing but the population average, meaning the national average profit of food processing industry is 17%. Whereas the average or the mean rate of profit in the selected companies from the Mysore or from the Karnataka, it is only 12%. and there are 20 companies, and comparing this company mean with the national average. So what I have told, I go with the test value. So ignore the sign. If the calculated t value is higher than the table value, then we can reject the null hypothesis. That's one procedure, what we generally do when we manually compute. So that is the manual procedure. But in the software, they give probability value. So don't go for the t value, go for the probability value. So this is the significance. The probability of committing type 1 error or the margin of error. So this is the probability. What it explains? It is explaining the probability of margin of error is less than 1%, because you have 0.000000, and somewhere it is 1 or 2 is there. Meaning your confidence is more than 99%, and your margin of error is less than 1%, so that you can reject the null hypothesis. So your t value, irrespective of sign, it's very high, and the probability of committing error is very less. You have a lot of very less, in the sense it is less than 1%, and the probability of the confidence, it is 99% and more than that, so that you have a lot of proof to reject the null hypothesis, and you are not making any error in making the decisions. So that, what is that? So now if you go back, or you can read the previous one. Now you can reject this null hypothesis and accept the alternative hypothesis. So alternative hypothesis is that the calculated, this is how you have to write in your thesis or in your article. This is how you have to write once you got this result. So the average or the mean rate of profit of the selected sample companies is 12%, and the national average is 17%. The mean difference is 4.88%. The mean difference is 4.88%. The calculated t value is very high, and the margin, the level of significance is less than 1%. So therefore, the difference between the two mean values, that is the sample mean value and the population mean value, is highly significant. So therefore, there are significant differences between the food processing and the rate of profit of food processing industries in Mysore and the national average. So this is how we have to interpret. Based on that, you can make any suggestions, right? So the next is comparing one sample with another sample. Look at here. You have two sample groups. Meaning you have some companies which are producing food processing companies, and there are companies which are producing some plastics or some medical are engaged in medicine related activities. There are two sets of the companies. Let me give one more example. There are two different districts. One is the normal district, another one is the backward district. What is the average weight of newly born babies in backward district, and what is the average weight of the babies in the normal district? And you also have another example, like we have two sets of the students. One set is male students, another one is female students. So you can also have another example, like consumption expenditure in rural area, in urban area, and also in the same like section A, section B. Also like the government school and the private school. Government school, what is the marks obtained in the government school, and what is the marks obtained in the private schools, like that. In English medium or in Kannada medium. So like that. You can give plenty of examples. Wherever you have two groups, that is sample groups. Sample groups. Sample means you have a group, and within the group you have many observations. Don't forget, this is not only one sample. You have a one group. Within that group, you have many samples, many observations. So you have class A, class B. In class A, you have 60 students. In class B, you have 60 students, or even 70 students. That's not an important issue. You maybe have different number of observations. Class A, 60 students. In class B, you have 70 students. So, okay, you have two groups, and in each group, you have many observations. And these two are taken from the same population, or the different populations. You may be taken from the same population, or maybe you can also taken from the different populations. So, and then you are making whether these two groups are the same or different. These two sample groups are the same or different. So in this case, we conduct two sample t-test. We conduct two sample t-test, right? This is the two sample t-test. And again, it's a parametric test. As I already mentioned, it's a parametric test, and we follow the t distribution. We follow t distribution. So I have mentioned here, reject null hypothesis. Look at here. If your confidence is more than this level, this is the rejection region, more than this, you can reject the null hypothesis. So here is the data I have. So again, I have the samples like income of food companies and the income of polymer companies, income of food companies and the income of polymer companies. Like that, marks of government school, marks of private school, weight of the babies, newly born babies in backward district, weight of the newly, like that. You can take any examples. The marks of male and the marks of female. So whenever you have a ratio scale variable for the two groups of the observations, then you have to conduct two sample t-test. So these are the data. If you are using SPSS for testing, then you have to enter the data like this. Income, like whatever the income I have for the companies, for all the 20 companies, first I mention the income of the food companies, and then I go for, in the bottom of that, I enter the income of polymer companies below that. So, and you are grouping the first company as the food companies and the second company as the polymer companies. So this is the procedure we use in SPSS. So only this way you can enter the data in SPSS. There is no other way. So once you have entered the data in SPSS, that will give you the result. Look at here. The income of polymer companies, it's 1,30,000 rupees, 30 plus rupees, and the income of food companies, it is 90,000. That is the mean value. That is the mean value, right? And then all the 20 companies are not having the income of 1,30,000 rupees, because you can see here the income of polymer companies are different. Okay, the income of polymer companies is different. The income of all are not have scored same. All are not scored same. The mean of the 20 companies is 1,30,000. The mean of 20 companies is 90,000. But all the companies under the food companies are not having the income of 90. They're having more than 90 or less than 90. And all the polymer companies are not having the 1,30,000. Some may be having more than 1,30,000. Some may be having more less than 130. Then I have to test whether the variance within the group, or between the group is same or not. So then for two sample test, conducting variance test for whether the variance are equal or not, that is mandatory. Only based on the F test, we move on to the T test. Okay, basically two sample T test is a T test, but while conducting a T test, as a precondition, you also have to conduct F test. So you have to verify whether the variance within the companies and between the companies are same or not. So in this case, the F test value is very high. The F test value is very high and significant because it is less than 0.05. Less than 0.05. Less than 0.05 means your margin of error is very less and your level of confidence very high. So therefore, you can reject the null hypothesis. So null hypothesis means equality. Alternative hypothesis, not equal. The meaning, the variance within the polymer science is different. The variance within the food science is different. The variance between polymer and food is also different. That's the first analysis you have to make. So take an example of a real example of students in A section of government school and A section in the private schools. In the government school, the marks is 45. Let me take one more example of the interesting example of cricket. Dravid, the average score in test is 50 and Sachin's average score is also 50. Are the any other? Sachin's average score in tests, in 10 tests, in 10 tests, Sachin has scored 50 runs in average score. Dravid also scored 50. Dravid also scored 50. Meaning there are no difference between Sachin and Dravid. But when I look into the scores of Sachin, in one match he has scored 0, next match he has scored 100, next match he has scored 5, next match he has scored 25, next match he has scored 10, and then next match he has scored 90, and like that he has scored 0, 5, 10, 15, 20, 100, 95, 90, 85, 80. Okay, that is the score, Sachin scored. Now come to the Dravid. He has scored 45, 46, 47, 48, 49, 50, 51, 52, 52, 53. He has scored. Sachin average is also 50. And then Dravid average is also 50. Now let me know who is more consistent in scoring 50 in the next match. What is the probability of whether it is Sachin definitely scores 50 in the next match or nearing 50, or it is Dravid? Anyone, can you tell me? Who will score 50 runs or near 50 in the next match?
Sir, can you repeat for a while?
No, there are two batsmen, Sachin and Dravid.
Yes.
Yes. Both have scored 50, average 50 runs in 10 matches.
Right.
Sachin also average score is 50 in 10 matches. Dravid's is also 50 in 10 matches.
Yes.
Sachin has scored in 10 match, first match 0, second match 100, third match 5, fourth match 95, fifth match 10, and sixth match it is 90, like that. And Dravid also scored in all the 10 matches. It is 45, 46, 48, 50, 51, 52, 52, 53.
Yes.
Dravid.
Then
Dravid.
what is the guarantee that?
Yes, Dravid is having
Dravid.
sir.
50.
Yeah. Because consistency is more. There is less variance, more consistency. Less variance, more consistency. So therefore, testing of variance is also very, very important in when we are comparing two groups. So therefore, even based on the variances, we can say the two groups are different. Okay. If you are moving to the t value, then the two groups are different. And again, even in the case of their average income, the t test value is very high and it is significant, less than 0.05. So therefore, the two groups are different as well as their mean value is also different. That is the argument. The two groups are different and their mean income is also different. The mean income is also different. So that's the kind of argument we can make. Let me go to the next one. It is the comparison of two groups of same observations of the same sample and populations. So example like the level of BP before and after. So whenever you have before and after situation, you have to conduct paired sample t-test, paired sample t-test. So it is like that. Before food, you have taken some samples. After food, you have taken some samples from the same population, same sample. So the two values for the same sample observations. The two values for the same Ramakrishna BP before food, Ramakrishna BP after food, Sita BP before food and after food, Salim BP before food, after food. Okay, Anita BP before food, after food. It is not different Anita, different Mahesh, different Ramakrishna, the same Ramakrishna. So like that, you may be how. For the science people, it is very good. You can have two different laboratory situations, use the same observations, conduct in two different situations, and you can draw the inferences. Okay. So whether this condition is different from other condition, like that. Like that, there are many examples. Here I have taken the examples like before and after. So before the marks is there, after marks is there. There's a teacher conducted a test. First he conducted for the 20 students, he has conducted the test. The students have scored like this. After some time, he has given some training to the students and he also conducted a test and the marks are there. Marks are there. For example, before this class, if you are asked to write a article on research methodology, what was the score you could get? After this class, if the institution has conducted a test and what is the score you will get? The same 31 respondents are the participants. Before this class, what was the score you could have get? After this class, what will be the score you will get? Make the comparison. This is called the paired t-test. And then let me move on fastly because I have to stop at 1. Okay. And here also again, look at here. The test value is 3.18 and the level of significance is also 0.001. Here also the margin of error committing it's very, very less. And there are significant difference between before and after. Meaning the mean score has significantly improved after conducting a test, after conducting a training, after conducting a coursework like this. The capability of the student has increased. So like that, we can make the argument. So therefore, conducting this kind of the workshop or the trainings is important for improving the research skills or the scores. The next circumstances is that when you have more than two groups, then how to conduct the test? So as far as I have told, there was only one sample group from the population, and there are two sample groups from the population, and then there are two sample groups, same samples, two different observations, and now we have three sample groups like this. Sample group 1, sample group 2, sample group 3. If this is the case, how to make the comparison? What test I can follow? What distribution I can follow? Unfortunately, there are no tests designed to make the comparison of mean comparison of more than two groups. Mean comparison of more than two groups. So for that, we have an indirect method of conducting the mean comparison of more than two groups, and that is known as ANOVA F test. ANOVA, analysis of variance, ANOVA F test. This ANOVA F test is meant for comparison of more than two groups. But there is a limitation, I will tell you. And the null hypothesis here it is, one of the group is differing from others. One of the group, meaning I have three groups here, I have three groups. Out of these three groups, one of the group is differing. But I don't know which is that group. Whether it may be a sample group 1, sample group 2, or sample group 3. I don't know which is that group. But my test design is only to identify one of the group is differing from other groups. And I'm testing this based on their variances. I'm testing this mean comparison based on their variances. When I use the word variances, obviously it is the F test, because F test is meant for the variance, but I'm making the mean comparison. Okay, I'm making the mean comparison based on the variances. The variances will help you to tell only which is the group, one of the group is differing, whether the groups are differing or not. Okay, only that. It will never tell you there is a mean differences. No, it will never tell you. The groups are differing or not. One of the group is differing from the others. And let me tell you, so F distribution, it's a very different type of the distributions it has based on their degrees of freedom. Based on the degrees of freedom, the shape of the curve is different. You can see the red line, blue lines, green line, and then brown line. And right side we have a blue line. It is the most normal line. In most of the books you can see this is the F distribution, but F distribution may be like this, like red coming down, going very high and coming down, almost like normal distributions, very highly courteous normal distribution, like that. F distribution may have any different shapes. And for ANOVA, again the same data I am having, that is income of polymer, income of food, and income of medicine. And again I am going to data in SPSS. In SPSS, I insert the data like this. I add the data like this. First one company, next another company, third one company. First company factor is 1, then second company factor is 2, 3, like that. So this is how I have to enter the data in SPSS. And then the ANOVA gives you the result like this. The ANOVA, it makes the theoretically what it does is it calculates the variances. It calculates the variances of each sample between the other sample, with the other sample, with the group, and with the total. So we calculate the three types of the variances. Three types of the variances: total variance, variance between the groups, variance within the groups. Total variance, variance between the groups, and variance within the groups. We could see sum of squares means variances. Sum of squares is nothing but variances. X minus x bar, square of it. X minus x bar and square of it. That is the sum of squares. Between groups, how much the variance is there? Within groups, how much the variance is there? And between groups, we had 3 groups. N minus 1 becomes 2. The degrees of freedom becomes 2. And we had 60 companies. 60 companies. Total is 60. Minus 3 groups. That becomes degrees of freedom within the groups. That is 57. Right. And the mean square is nothing but sum squares divided by degrees with their respective degrees of freedom. You will get mean square. If you divide the mean square of one by another, it is not, there is no such rule that you have to divide the between groups variance by the within groups variance. You can divide which is the bigger value, you divide that by the smaller value. That is the only rules. And the F value is very high and very significant. Significant means you are committing very lesser amount of error, so that you can reject the null hypothesis. So the null hypothesis is that none of the group is differing. Alternative hypothesis, one of the group is differing. So that now you are rejecting the null hypothesis, which is none of the group is differing, and you are accepting, yes, at least there is a group which is differing from others. But as I said, the limitations of ANOVA is that which is that group we don't know, which is that group we don't know. So for that we need to move for another test which is called multiple comparison test. Multiple comparison test, again the same thing, I have different values. So rural, semi-urban, urban, it is the income, just I given the name income. So income, this is Duncan test, and this is homogeneous subsets. It gives homogeneous subsets by using the harmonic mean method. So the Duncan gives you homogeneous subsets, meaning if the values of the different groups are the same, then it will be in the same group. If the values are differing significantly, then the different subsets will be created at 0.05 level of alpha. Alpha means level of committing type 1 error, that is the level of significance. So like that, the multiple comparison Duncan test will create subsets. If there are 3 subsets, meaning there are 3 different groups. There are 3 different groups, and it also gives their average value also, the mean value also. So therefore, Duncan will help you to make the comparisons. And there is another type of the data, as you have already mentioned, nominal data. So for the nominal data, we have 2 types of the test, and the one test is like that. Is there any skew between yes and no? As I said, are you satisfied with this class? Out of 40 members, 29 have told yes sir, we are happy with the class, but 11 have told no sir, you are not fully happy. You are not fully happy. They are not saying unhappy. You are not fully happy. Okay. So 7 said not fully happy. 29 said yes sir, fully happy. Meaning no, it is 27%. Yes is 72%. But I have a doubt to state that the class was good. I am afraid of saying that the class is good, because there are people also said the class was not completely good. Then what I do? I conduct a test. So here I have the test. Okay, I conduct the test, and that is goodness of fit test. Chi-square goodness of fit test, and that test value is high and significant. Therefore, now I can say the opinions are significantly skewing towards yes. 72.5 is significantly a big number compared to 27, or the 29 is significantly a big number compared to 11, that is the smaller number. So therefore, the class is good, or the class was good. Now for the curiosity, just I want to know, how could I know whether the male have said yes or the female have said yes, largely said yes. For that also I conduct another test called chi-square association test. Chi-square association test. Look at here, out of 20, only 2 males have said no. 18 males have said yes, which is almost 90%. Whereas, as far as female is concerned, out of 20, 9 have said no. 11 have said yes. So then I conclude that the probability of the class become more interesting and good, it is more for the male compared to female. So therefore, then I have to use some techniques or the tactics to reach out the female participants also. Like that you can make the, yeah. So the next is the establishing the relations. For that, we always conduct the correlation test. And there are a lot of correlation coefficient test we conduct. And first we compute the correlation value, degree coefficient value, and then we test whether that correlation is acceptable or not. Like that, we also have the impact analysis for both numeric and nominal data, impact of investment and development, impact of rainfall on food grains production, impact of region on education, and many econometric tools that we can use to analyze the impact of the variable, one variable on another variable, and the multiple variables on the other variables. So these are the impact, and there are plenty of impact analysis. And most of the previous examples, whatever I have given, that is meant for the cross-section data. So there is another type of the classification of data based on their structure. If the data is collected at a point of time for more than one observation, it is known as cross-section data. Most of our primary data, it is a cross-section data. Sometimes you also get the data like 2001, 2002, 2003, 4, 5, 6. Like this is known as time series data. Whenever you use time series data, if you get any results, particularly using the impact analysis, whatever the results you get, most of the results are spurious. Spurious means looks like very good, but really they're not having any meaning. They're not having any meaning. So that is called spurious results, spurious regression results. So therefore, if the data you are using this time series, you have to check whether the data is stationary or non-stationary. If the data is stationary, then no problem, your results are not spurious. You can go for estimating the impact. And you can use OLS method, ordinary least square method. If your data is non-stationary, then you cannot use that data for the analysis. There you can go for the non-stationary kind of analysis like co-integration analysis and the RDL analysis. These two methods are help in establishing the long-run relationship between the variables. So that if your data is time series, you have to be very careful whether the data is stationary or non-stationary. If it is stationary, you can go with regular procedure. If it is non-stationary, you have to go with co-integration or ERDL. ERDL means auto-regressive distributed lag model. And there are some advanced classification analysis like data reduction techniques, factor analysis, principal component analysis, and other principal component analysis. We have many rotated analysis. We have creating components, multiple regression analysis like higher order. You can go cluster analysis, randomized impact analysis, and you also can go for these structural equation models. In recent years, many people are using these structural equation models. So particularly in management and commerce, in social work, they are using the structural equation models because the relations are multiple and multi-complex. When the relations are multiple and multi-complex, you cannot go with one-way kind of the relations. This will influence this, this will influence this. You cannot go. This may be influencing this, and this may be influencing that, and another may be influencing another may be influencing another. Father education influencing the son education influencing sister education influencing the teacher education, or teacher education is influencing the student education. There are multiple and multi-complex relations. So therefore, for that kind of the relations, it is always better to go for structural equation models. Sorry, I have only 2 to 3 minutes for a discussion. I have taken almost your time. If you have any queries or the questions, or if you wish to add something to the presentation, if you wish to say something about how to improve my class, or if you need anything extra, please.
Sir, namaste.
Namaste.
We had a fantastic session so far, sir. Anybody can easily understand by your presentation. Thank you very much.
Thank you, Mahesh.
Before that, I would like to ask one thing.
Yes.
While forming or while going to a particular research work, we
Yes.
have to carry some hypothesis, what you have said,
Yes.
null hypothesis and alternative hypothesis.
Okay.
In the test, we have to reject the null hypothesis and accept the alternative hypothesis.
Yes, sir.
What are the minimum criteria for having or while framing such hypothesis, either for null hypothesis or for creating